Hey, what's going on, folks? It's Mike here, and welcome to our next lesson in the Modern C++ series. In this lesson, we're going to go ahead and continue our discussion about casting. So I've had a few previous videos on this topic, so feel free to check those out in the playlist, but otherwise, let's begin talking about casting in Modern C++. And when I talk about casting in Modern C++, I really mean the 4 different types of casts that were introduced in C++ 11. And there's also been one in C++ 20 called bitcast, but I'm not exactly going to talk about that. So without further ado, let's go ahead and take a look at those casts here. So what I'm going to go ahead and do from C++ reference, just look at the keywords, search for cast here, and you'll see that there's a few different types here. So let me go ahead and zoom in so you can see we have dynamic cast, we have reinterpret cast here, we have static cast, and if I go down here, we have const cast. So the one that I really want to focus on today, or the two rather, is dynamic cast and static cast. So we'll take a little bit of a look on that. And if you want to see more such as const cast and how reinterpret cast are used, maybe I can do another video. Just comment below if that's something you're interested in. But the reason I'm going to focus on these 4 named casts is that, well, they're really nice to know about in C++ because they describe what your intent is. Now, the regular C style casts that we can do for a data type in effect are going to try out these different casts here in a modern C++ compiler. So there's a certain order where they might start with, for instance, seeing if it can pull off a static cast and then sort of going down all the way to doing a reinterpret cast, which is basically just saying, hey, treat these bits exactly as I'm telling you to. And that's the basic idea. So we do get a little bit of type safety from the compiler by trying out these casts. So without further ado, let's just go ahead and look at static cast here, so we get an idea of what it is. And as it says, it converts between types using a combination of implicit and user-defined conversions. Now, sometimes we can just convert between a type, like an int and a float. For instance, that's easy to do. And in fact, I'll go ahead and show you an example in a moment of just converting between the integer and using a floating point number, where we can just truncate off the decimals in the floating point number. So just to illustrate exactly what I mean here, let's say I wanted to treat 3.14 f here, the floating point value, as an integer. One way that we learned previously to do this is that we could just cast this value to an int here by typing out int right in front of it, the actual type name, and that will effectively just get rid of everything after the decimal. So that's something that we can sort of do relatively easy. Now, there are different types of casts that we can also perform if we have a constructor, for instance, where we could, for instance, do this on assignment for a non-primitive type. And I might actually leave that to another video, but that's what this is getting at when it's talking about implicit and eventually explicit user-defined conversions that are allowable. Okay, so that's static cast. And again, the idea is a static cast is we're going to try to figure out at compile time if we're able to perform this cast. So if I have some sort of hierarchy, and let me bring up my whiteboard here again, and let's say we've got some base class here, and then I have a derived class, I can try to determine, can I treat this derived class as this base class? For instance, the compiler has enough information to figure this out. So this is something that we could use a static cast for instance. But on the other hand, could we treat this base class as a derived class? Well, again, that's something we can also figure out at compile time. I'm going to show you how that works in a moment with some code examples. But let's go ahead and just take a quick look at dynamic cast here so we can see how this works. Now, dynamic cast is similar in a sense to static cast in what our goal is to treat one data type as another. But this works with pointers and references. Okay, so that's one of the key differences for the different types that we are converting here. And the idea is that we can safely convert these types here along the inheritance hierarchy. Okay, and the word safely here basically means that dynamic cast will attempt at runtime to do the conversion, and if it fails, then it will return a null pointer. So you can essentially have an if condition. So again, let me go ahead and illustrate what this would look like. So I could have something like if, and then I could do dynamic. Let me just abbreviate this. Actually, let me write this just down here. So I could do if dynamic underscore cast, the type that I want to cast to. And in this case, let's just go ahead and say derived, and it has to be a pointer type, so the asterisk there. And then the thing that we are casting, so I'll put base here, for instance. And if this is possible, then I can execute this code here. So you can see how we have this extra check here. Now, if this isn't allowed and we try to do something with this particular data here, then we'll get a segmentation fault. So again, we can capture this information. Now, in order for us to be able to do this and sort of explore the hierarchy, since we're working with pointers, we are going to need each of these classes to have a vtable. Okay, so I'll just put here a little vtable pointer, which would, of course, point out to let us know which correct virtual functions to call and so on. Okay, so I'll try to illustrate this with some of the examples today, but just know that we would need something virtual in this base class to do this. And again, these need to be pointer types. And typically, as far as I know, to the best of my knowledge, we need RTTI, which stands for runtime type information, to figure out, well, is this a valid conversion? So I can already kind of tell here that dynamic cast is doing a lot more work here. So maybe to quickly summarize, static versus dynamic cast versus dynamic. This is more expensive. It works with pointers and references, with pointers and references. And I'll just mention today in my examples, I'm only going to be showing with pointers, but this will also return a standard bad cast with the references if you use them, if you're trying to catch what's going on here. Here we get the null pointer if we're just using a pointer type here, but with a reference, we would be able to handle bad cast here. So static, less expensive, sort of more dangerous, I guess. And at compile time, we can usually get more information if this is going to be legal. So ideally, this is something that we could try here. Okay, so that gives us a little bit of an idea of some of the things that we have available with static and dynamic cast. And again, the idea with a C-style cast, and I'll just kind of put as a note here, note, C-style casts in a C++ compiler essentially try all these casts. And if you want, you can go ahead and take a look at that. But what I mean by all these casts, meaning that typically first it's going to try, I believe, a static cast, and then it might also try const cast, and then maybe dynamic cast, and then maybe it just kind of gives up at the very end of the hierarchy and just tries reinterpret cast and says, okay, treat these bits as whatever type you want. Okay, and that's the idea here. Okay, so there's a little bit of a hierarchy that you can search there, but I think I want to show you or start showing you some examples and a little bit of motivation with static and dynamic cast here. Okay, now, again, I'll give my disclaimer when I talk about casting here in a moment here, that in general, and as I have at the top of my notes here, and I'll make this a little bit bigger for you so you can see here, the idea is from our core guidelines, we want to avoid casting where possible. Just because, again, if you're trying to change representation, maybe that is in fact some sort of code smell in a sense of, well, you're changing types. We know it has some kind of cost to at least traverse a hierarchy and figure out if it's valid, or at least at compilation, if we can do this sort of cast. So again, we try to avoid it. Sometimes we just can't, right? We just have to, or we don't know what the input's going to be. And my general recommendation is, prefer dynamic cast if you must, because at least you can check if it's valid and get some sort of error handling. That is, of course, you really, really need performance and don't have any runtime. You want to get rid of your runtime type information. So for instance, in games, you might not want to have to pay that cost or carry that extra information with your classes. So again, we have to think carefully about this. And in order to help you think a little bit more carefully, we do have the core guidelines, which is the last thing that I want to show you before actually showing some code here. So ES49 on the core guidelines, and then we have a few more starting from C146. So let's just go ahead and take a quick look at those. ES49, in fact, confirms if you must use a cast, use a name cast. And again, these are sort of the reasons. And I believe these are the orders that some of these casts are used. You can see that there's some other ones here, narrow cast, some other ones from the GSL library. And as I mentioned in C++20, there's also a bit cast if you need that. And then, of course, there's C146 that just goes ahead and talks about some of the different casts here with dynamic casts, which is one of the things that I'm focusing on this lesson. So that's where you can look at more, but let's go ahead and just kind of walk through some examples to make more concrete some of this casting stuff here. All right, so I'm going to show you these classes in a moment, but let's just go ahead and start with something simple. Okay, again, just our C-style cast here. And again, our C-style casts, as I say, they're almost too liberal in that they just kind of let you do whatever you want here. So if I go ahead and try to compile this, and again, you don't need C++20 for this style of cast here. This one actually will give me an error here, where I'm just saying, hey, this pointer is set to this address. But, you know, you can override these things by doing F permissive, which I don't recommend doing, and then it'll just give you a warning, right? And we could actually run this and it'll generate some sort of result. Maybe this address just happens to be legal, or, you know, again, we're sort of casting things around here. Again, probably pretty dangerous that you'd want to be doing this, especially with a pointer type. So again, you know, that's just maybe a worst case for a C-style cast here. So let's just go ahead and move to demonstrating a static cast here. So what I've got for this example here is sort of similar to our other examples. So I've initialized F here as a float. So this looks good to me so far. And then here I'm just going to say with I static cast int F here, and then just go ahead and compile, and let's go ahead and run this, and you can see that it's 3. Now this is going to work fine with your C-style cast again. And even if I get rid of all this sort of casting here, let's just go ahead and recompile, rerun. You see that we get the same result. It's pretty safe, right? The compiler can make this sort of implicit conversion on these primitive types without problems. So why did I go through the trouble of doing this static cast here? Well, you know, this is more searchable. You can grep for a static cast. Again, that's sort of a reason to use this style. So for this particular example, it's maybe a little bit overkill, but I would prefer, again, to, it's just easier to search. And again, I could do this same thing with the C-style cast. But again, if I just sort of leave it as int and then F here, it bothers me because this kind of looks like the C-style function pointer syntax. So again, I just don't really like it. So if you have access to a modern C++ compiler and can do C++11, I really like you know, using this instead where you must. Okay, so with that said, let me go ahead and comment back out this example here, and we'll go ahead and move on here. Now, before I move on though, let's go ahead and start talking about where casting gets a little bit more interesting, where we have some actual classes here or types here. So I'll go ahead and reveal those to you. Let's just go ahead and show you for a minute that I'm going to create these derived and base classes here. So what do I have here at the top of my code? I have a struct here with base. It's got one integer here that it stores. And then I'll have a derived class that also is derived from base, and it's got its own derived data, which is set in the constructor, and the base data, which is also set in base's constructor here. And then they'll each have their own member functions called do. Okay, so that's the idea. So just to make things a little bit easier for you, let me go ahead and split this window here. I'm going to go ahead and open this up again. Let's do it for read only here. Just one moment. And let me go ahead and I'll try to keep these just within scope here, just so you can kind of see them. But these are the two classes that we have here, just so you have an idea. I know I'm blocking it just a little bit here, but again, there's really not super interesting stuff going on. But anyways, this is our hierarchy. So let's go ahead and focus on our casting now. And what I'll go ahead and do is just show you that this scenario is allowed. So I've got my derived class D, base class B. I can call each of their appropriate member functions here. And if I want to treat D as a base, I can do that here, okay, for this concrete type. So let's go ahead and try to compile this. I'll go ahead and run it. And you can go ahead and see that when I call D's do member function, I get 22. When I call on base a function, it prints out its data 11. Again, that's what's initialized here. This derived class to 22. And when I'm doing this static cast here, well, I'm saying, hey, treat D as the base class, but call the do function here. And then we can see that, well, the base is actually what is being called when I'm using this derived type here. So this is kind of interesting in how this works here. Now let's go ahead and just play around with this just a little bit here. And maybe if I add, say, virtual, let's see what happens here. So now, let's see if I rerun this, do I get the same thing? Well, I still get the same thing here because these are just concrete classes here. So again, we do have to think about the type that were initialized here. So this isn't changing here. I'm just saying, hey, treat my drive class as base here and just literally call do here on it. Okay, so that's the idea here for that one. So let me go ahead and get rid of virtual. Oops, let me actually add it to base here. That's what I meant to do, just to show you the experiment. Again, it doesn't change anything here, okay? So let me get rid of the virtual for both of those, and we can see how this works. Now, there is one line here that I want to uncomment here. And let's go ahead and see if we can do sort of the opposite here and say, hey, can we treat the base class B as a derived type? So we're sort of moving down the inheritance hierarchy, if you want to think about it that way. And let's go ahead and try to compile it. And at this point, you're going to see that there is, in fact, an error here. I'll try to make this a little bit bigger just so you can see. It's going to make my layout go a little bit wild here, but basically it says no matching function for call to derived for the base here. So here is where we would need some sort of explicit destructor defined that could do this actual conversion. Okay, it's not going to traverse the hierarchy for us here. Okay, you might want to provide that actual conversion, but in this case, I have not, right? So you need a constructor that looks like this in the derived class. Okay, so that's a good exercise for you to do if you want to try that out here. Okay, so let's go ahead and comment this one out then. And let's go ahead and move to our next example. Now in this one, I'm going to go ahead and use pointers for our types here. Okay, so let's walk through this one a little bit carefully here. So I've got my base class B here, and I'm going to create it as base here. And then I've got my derived, and I'm going to create it as derived here. And then again, let's do the static cast. So this time I'm saying, hey, for B, I want to treat it as the derived type here. And let's go ahead and try to compile this. And let's try to run it. And let's see what we get here. So here, my base class here, I'm saying, hey, treat it as derived and then call do. So I do see that there is a call here. And I'm comparing that with just my derived class when I call do here, which is called. But the information that's set here is kind of weird. There's kind of something funny going on here. I get 22 and then I get a 0 here. So this is a little bit strange behavior with our cast. And again, showing you why casting is sort of dangerous in this situation here. So what's going on? Well, we can kind of see that, this is kind of following that previous example here where I said, hey, this is kind of weird when we did this conversion here, right? We're trying to treat B as a derived class here. But if we don't have any vtable information, then I guess, this is being allowed to happen, but it's not really giving us the right information. So let's see if we do have a little bit more information. What we really need is a vtable in our classes here so it can kind of convert or do the right thing, right, when we have a pointer here, right? Because base, or I should say derived, is a type of base here. Okay, so let's give ourselves a vtable here. So I'm going to go ahead and scroll up here. And how would I do that? Well, let's just make this virtual. And that gives us a vtable. I can also, I could mark this as override, but let's just make this virtual right now. Okay. And let's go ahead and see what the behavior is. Again, kind of keeping track and saying, well, are we going to get the right do function call here? So if I'm treating b as derived, let's see what happens here. So I'm going to try to recompile this, rerun it. And then again, interestingly, if I compare here, let's go back to our result here. This time, since I have base here that's being called here versus this first one, it is just calling, well, base's do function here, but we've actually got the data here that we need. So we can kind of see that static cast isn't really giving us much here. It's just kind of saying, well, we're going to follow up, the chain here and treat b as a derived type, but, call the base function here. I mean, let's even experiment. Let's say, well, what if we, let's make this, virtual. Let's override it. And let's go ahead and see if the derived class is called. Again, I'll compile it. I'll run it. Still nothing here, okay? So the static cast isn't really getting us much here, okay? So let's go ahead and see if we have another tool that can help us here. Okay, so I'm going to go ahead and comment out this experiment. And let me go ahead and just, get rid of this here. And let's compile with our next experiment here. And this time we're going to take a look at dynamic cast. And again, this one only works with pointers. So we were working with pointers before. And let me go ahead and, this is a little bit of a larger example here, but let me walk you through what's going on. So the top looks the same here. I've got a base here, B, and I'm just creating as base and derived with D here. Okay. So the first thing that I'm doing is just checking what are valid casts, meaning can I treat the base class as derived and can I treat the derived class as a base? So again, we have to sort of think if we're moving up or down the hierarchy. So again, looking at this diagram here, at line 107 here, so that's this first case here, let me illustrate. I'm saying, can I treat this base class here as, something further down the hierarchy? And in the second case, can I treat this as a type of base here and actually make some sort of call here? Okay, so let's see what happens here. Because before, well, where we got in trouble with our static cast, well, I had this case here, which is matching exactly this case here. But this time the difference is I'm doing a dynamic cast versus the static cast. Okay, now we got weird behavior before when we were doing this. So let's even see if we get into this condition here. Okay, so let me go ahead and make sure I save. I'll go ahead and compile, and I'll go ahead and run it here. And let's see what happens. Well, the first thing that I get is this message here, treating D like base here. Okay, so that means this condition wasn't valid. Okay, so even though this sort of allowed us to do something kind of funky with our pointers, maybe it wasn't even allowed. Well, in fact, I'm showing you it's not allowed. And that's the advantage we get with dynamic cast. If you've been watching this far into the video, this idea that we can check here, this would return null if it's not allowed. So in fact, this returns null. We never go into this condition here. Okay. All right, so let's explore what the rest of this code is doing and printing out here. So let's go ahead and see the condition that works here. So we are treating D like the base. And then I just call on D the regular member function here, without any sort of cast here. And because this is part of the hierarchy, and you can watch my videos on object-oriented programming and calling into a specific version of do, I can call from my D, my derived class, the base version of do explicitly, which is what I get here. And then I can get to base's data. And the derived, which I can then get at do's point of data here. And now that I know this cast is legal, I could just, do the static cast here. Okay. And that's what I'm getting down here. Because I know I'm allowed to go from this derived type to the base when I'm converting these pointers, I could explicitly call this member function if I wanted, access to that specific member function to, treat this data differently here. Okay, and then finally, I just go ahead and show you that, well, from my derived class, even if I'm treating it like a base, when I call the do function here, it's not, really changing the effect of the virtual call. Okay, And that's kind of something important to realize with these dynamic casts, with how we're sort of treating stuff. And it might be worth you actually going through an example where you create a little bit more of a complicated hierarchy with different sort of branches. So when you're trying to treat some set of bits as some other set of bits, you can think about this just a little bit more. But again, just notice that even when I do this cast here, it's not changing everything. Now you might say, well, let's go ahead and try with dynamic cast. And then we're going to go ahead and watch and see, does this remain derived or does this change to base here? Okay, I'll go ahead and rerun this. It works. Again, nothing changed here, okay, because we're still this type here. That's how we initialize D as derived. So it's going to call that do function unless we explicitly call this base function. So again, what was the point of this exercise? It was for me to say, hey, is this valid? Do I know that this thing is, part of my hierarchy so that I can explicitly call, a different member function along this hierarchy? Maybe it is something that's been overridden, right? As we've done in our actual code here. Okay, so that's the idea. Okay, so I'll change that back to static cast here. Let me go ahead and uncomment these or comment these and do another example here. Okay, so this will be the last one because, this is a longer video than usual here. And let's go ahead and try something out kind of fun here. So what I want to introduce is, let me go ahead and, there we go, get rid of these lines here. There we are. I have this derived class D here, and let's go ahead and create this. And again, just scrolling up to our previous example, right? D we can treat as base. Okay, so that we've proven, so we can get away with this static cast here. But again, let's just see what happens if I do the C style cast here with some unrelated class here. Okay. Now it's unrelated in the sense that if I scroll down here, this isn't part of the actual class hierarchy, right? It's some other representation. It's got a float instead of an integer that's storing, right? That's how our derived and base classes were with these ints here. I've just got some sort of floating point data here. It's got its own member function do, so it sort of matches. It sort of looks like it, but it's not on that hierarchy. Let's go ahead and see what happens when I do a cast here and then just a C style cast of the unrelated thing here. Okay, so it's going to allow me to do it because again, at the end of the day, the C style cast might just say, hey, no matter what, treat these things as they are. And when I run this is kind of interesting because I get 22 here. But here, when I try to cast, D is just some random, type, unrelated. Structurally, it looks similar. So you're kind of saying, hey, maybe I could cast this thing. But we essentially just get nonsense here in the value that we are printing out here, right? We would expect some sort of, floating point type here or whatever. Okay, and just to again show you why we use the name cast in C++, let's try to do a static cast here. The compiler would catch this and say, hey, these things, aren't really allowed. We can try this again with a dynamic cast. And in this case, it's going to compile because dynamic cast is a little bit more flexible, but we will get a segmentation fault that eventually says, hey, this thing truly should never have been allowed. So that's the idea here. When you have some unrelated type here, you could try reinterpret cast and maybe it'll do sort of the right thing. Let's go ahead and try it. Reinterpret cast here. Let me make sure I spelled this right. Add one more R here. And let's just go ahead and see what the behavior is. So it'll compile, it'll run, but again, it's just giving us essentially nonsense at this point here. And we can kind of see that the C style cast eventually had to resolve to this reinterpret cast, which just said, hey, no matter what, treat these bits, we've got a matching function here. So let's see if we even change that function here. Again, just to kind of play around with this, if it would just still try to do something, it shouldn't here. So let's just say don't. In this case, it should say, can't find, some sort of related thing here. But again, just depending on how your code base is structured, you might run into these cases here. So again, just to show you, what we should have done here, maybe a static cast or a dynamic cast here, but with a caveat where we say if, this fails, and I would go ahead and maybe just do this check here, something like this, then we at least won't get the segmentation fault and our program will keep running. Okay, so let me go ahead and put that back to how it was so that we have our code in a decent state here. And I'll go ahead and comment this out. And I'm going to scroll through it one more time just to give us a recap. I know this video has been a little bit long, so thanks for your patience. But essentially, the idea is if we can avoid casts, we try to avoid them because they can be a little bit dangerous. But we do have this cool thing, dynamic cast, at least when we're working with pointers or reference types that will help us write some more safe code or catch which casts might not be valid. And again, they're more easily searchable. The 4 keyword casts that are built into the C language, the modern C++ language, that is. And then, of course, there are bit casts and narrow casts and other things that you can look into as well. So I think I'm going to go ahead and cut off the video here since it's plenty long, and just thank you for watching if you made it all the way. If you made it all the way, just go ahead and make a comment and feel free to ask some questions. So we can go ahead and see that when you're converting data to different types, it's something that we have to be really, really careful with. Sometimes it's unavoidable. Sometimes you're just reading blobs of data and you have to sort of know with some domain knowledge how to convert data. And again, that's fine for your use case, but you might want to try to see if you can fit that data into some sort of structure and then test it with dynamic cast, for instance, just to see if it's going to be valid. All right, folks. So with that said, I hope you enjoyed this lesson. Again, thanks for your time. I won't take another second, and I'll look forward to seeing you in the next video.